No! Floor function! No! Don't tell me. Ooh. We have a floor function inside an integral, and it's not even an easy integral. You're going all the way to infinity. And that's way too far away, at least for me. So this integral is freaking me out, and maybe it is disturbing some of you guys mentally also. Whew. So how do we even start this? Well, if you examine it closely, integral of x times e to the 1 minus x seems possible. And the reason is because we know how to integrate things like x times e to the x dx. We can integrate things like x times sine of x dx. And I'm talking about the functions where you have algebraic function multiplied by transcendental. So x is algebraic, sine of x, e to the x, cosine of x, all of those are transcendental. And whenever these two are multiplied together, as we learn in calculus 2, you can use integration by parts. So integration by parts, sometimes, not always, but it works out a majority of the time. So x times e to the 1 minus x, it seems like we can do that. We can try to do the techniques of integration by parts to maybe simplify this. But we have this crazy floor function, and I'm not quite sure how to start this yet. So let's begin with the part that looks easy. So let me start by splitting this up. Integral from 0 to infinity, x times e to the 1 minus x dx minus integral from 0 to infinity, and now you have a floor function times e to the 1 minus floor of x dx. And for those of you that do not know what floor is, let me mention that really fast before I go on. This is called the floor function. Floor function, as you can see, because these brackets are making a floor. You don't have any ceiling, you only have the floor. That will be considered a ceiling, but we don't have those. You're only looking down. And floor function, it's also called greatest integer function. Let me write that too. Greatest integer function gets you the greatest integer less than or equal to x. Greatest integer function. Another way of thinking about it, greatest integer function gets you the smaller or equal value right next to x. That's one way of thinking about it. Smaller or equal integer value, I should say. Integer value right next to x. So I can say floor of 1.1 is going to be 1, because if you drop down, the first integer you're going to hit or encounter is going to be 1. Floor of 2.7 is going to be 2, because if you go down, the first integer you're going to hit from 2.7 is 2. Floor of 3 is going to be just 3, because it can be equal. 3 is the integer to begin with, so that's going to get you 3. So that's greatest integer function, just in case you guys do not know. And maybe now you see why this is so crazy, because we can't just anti-differentiate a floor function as easily as things like x dx. Anyway, now let's focus on this part. Integral from 0 to infinity of x times e to the 1 minus x dx. Well, e to the 1 minus x dx is same thing as e to the first power times e to the negative x. I'm just splitting this up. Remember, if you have e squared times e cubed, they add inside 2 plus 3. In our case, we have the addition to begin with. You have 1 minus x, and you're just splitting it apart, just in case you guys did not see what I was doing. So this integral, let me actually focus on this left integral to begin with, because that's the one we are working with. So let me write that. X, and you have e times e to the negative x, and e is constant, so let's bring that out. And you have e to the negative x dx. So now we gotta integrate x times e to the negative x. Now let's use integration by parts. And how should we pick u and dv? Well, you usually pick u such that it simplifies. When you differentiate it, u is going to simplify. You usually want it to simplify, not always, but that's one guideline to follow if you're really confused. And v has to be something we can integrate. you have to be able to integrate it. So in the case, let me show you an exception. For natural log of x dx, for natural log of x, you cannot integrate it yet. I mean, that's the entire point to integrate natural log. So natural log of x has to be u. But in our case, e to the negative x, we can integrate that. So dv can be e to the negative x dx. And our u is going to be x because when you differentiate u, it's going to simplify. You simply get 1 or 1 dx. Anyway, now you gotta integrate dv to get v, and that's going to be negative e to the negative x, because when you differentiate negative e to the negative x, you should get negative e to the negative x times negative 1, which is e to the negative x. So we know v is negative e to the negative x, and du is dx. So now let's use integration by parts. If you guys remember, integration by parts tell you integral of u dv, which is what I have. That's u, this part is dv, is equal to uv minus integral of v du. And we can just plug in the values now. E times, so let me actually focus on, you know what, let me just write it down. uv, that's u, that's v, so let's multiply them together. Negative x times e to the negative x, and minus integral of v du, and v is negative e to the negative x, and let me just cancel that negative with this negative to make positive. So you had negative sign, but v also had negative sign, so I'm just making that positive. Anyway, e to the negative x, and du is simply dx, and now we can integrate this. And remember, you're going from 0 to infinity on this. E times negative x, e to the negative x, and integrating e to the negative x as we have done gets us negative e to the negative x, and you're going from 0 to infinity for this. If you guys are still not seeing how we integrate the e to the negative x dx, think of applying u substitution with u equals to negative x, such that du is negative dx, and I'm just plugging in negative, and I'm now doing e to the u du, and that simply gets us negative e to the u or negative e to the negative x. Just in case you guys were confused by my logic, that's how I'm getting negative e to the negative x. Anyway, so you're going from 0 to infinity for this, and when you plug in infinity to this, e to the negative infinity is going to be extremely small, more so than x, because e to the negative x is going to approach 0 faster when you plug in infinity, when x is getting extremely large, because that's an exponential function. That's going to dominate, and that's going to approach 0, that's going down, so you get 0 on this side. Same reasoning applies for this one. Now let's try to plug in 0. Well, when you plug in 0 to negative x e to the negative x, you have 0 times e to the negative 0, that's simply 0. And you also have 0 minus e to the negative 0, which is 1. So this entire thing evaluates to e, and you have positive 1, so it's just e. So we have figured out this left part. This entire left part is e. So now we just gotta figure out how to deal with this thing. Okay, so let's try to deal with this floor function. So let me rewrite that. Integral from 0 to infinity of floor of x e to the 1 minus floor of x dx. Okay, so let's go to a new page and let's try to attempt this. Well, one way you may say is we have to find the antiderivative. So we can plug in 0 and infinity and try to somehow find the value. But how are you going to anti-differentiate it? It's not very obvious to me, at the least, how we can start it. Because this floor of x is not going to vary as much as x is. But what do I mean by that? I mean the floor of x, when you plug x equals to 1, you're going to get 1 out of it. When you plug in x equals to 1.01, you're still going to get 1. When you plug in x equals to 1.9, you're still going to get 1. It's pretty resistant to change in x to some extent. Well, trying to find antiderivative, I don't see any way right away. So why don't we try to think about this graphically? See what the definite integral is asking us to do. So how do we graph this function? So f of x is equal to floor of x times e to the 1 minus floor of x. Well, if you think about it, between 0 and 1, floor of x is going to get you 0 because you're going to drop down to 0, not including 1, of course. So you're going to have 0 times something, and that's going to be 0 from 0 to 1. So this function has area of 0 from 0 to 1. And hey, maybe we have just figured something out. We realize the area is 0 from 0 to 1, and maybe we can do similar things, construct rectangles on and on and on, and instead of trying to find antiderivative, maybe we can try to add up the areas of these rectangles to find the definite integral, because after all, definite integral when the function is positive is simply the area under the curve. We don't have to go through all the fundamental theorem to find the area, not always. So maybe that's something we can think of. Anyway, let's continue this reasoning. From 1 to 2, our floor of x is going to be 1. You're dropping down to 1. So you're going to get 1 on this side. And you have e to the 1 minus floor of x, which is 1. And that's e to the 0, or also known as 1. So from 1 to 2, your function is going to have the value of 1. Okay? So the area you want to find from 1 to 2 is this. That's the area we want to find. Let's continue this. This is very fascinating. Between 2 and 3, the floor of x is going to be 2. And just substituting the values in, you have 2 times e to the 1 minus 2, or 2 over e. And the question is this less than 1 or greater than 1? Well, if you look at this, e is more than 2. E is about 2.71828182845, and it goes on and on and on. And since e is greater than 2 over e is going to be less than 1. So we have between 2 and 3, we have this another rectangle that looks something like this, and the height is going to be less than 1. Let's continue. How about between 3 and 4? Between 3 and 4, our floor is going to be 3. So our function is going to be 3 times e to the 1 minus 3, also known as 3 over e squared. So in this case, you are increasing the top, of course, but the bottom below, between 2 and 3, you're multiplying by 1.5, but going from e to e squared, you're dividing by e, which is 2.7. So you're dividing more than you're multiplying, so the height is going to decrease once again. And obviously, the height is going to decrease every single time, because every time your number above is increasing by plus 1, but if you're looking at that from multiplication point of view, you're not increasing by a lot. For example, the next one is going to be 4 times e to the 1 minus 4. Following this pattern, you have 2, 3, 4, 2, 3, 4. So next rectangle is going to have a height of 4 times e to the 1 minus 4, which is 4 over e cubed. Going from 3 to 4, you're multiplying by 4/3, but you're dividing by e once again. Obviously, the number you're multiplying is small compared to the number you're dividing by. So the height of each successive rectangle is going to get smaller and smaller, which makes sense because we need this integral to converge. For the sake of MIT integration B, I don't think they give any integrals that diverge, as far as I know. So that's how this integral looks like. And we gotta find sum of all of these areas. If we can find sum of all of this, we have our solution. So how can we? Well, these are rectangles, and how do you find the area of a rectangle? Well, that's just the base times height. And the base is always 1. That's 1, that's 1, that's 1. So we only have to worry about the height. And the height of the first rectangle is 1. So the area of the first rectangle, let me write it like this, a sub 1, a sub 2, a sub 3, and so on. So area of the first rectangle is simply going to be 1. How about area of the second rectangle? Well, that's going to be 1 times the height. And for the second rectangle, height is 2 over e. So 2 over e. And area of the third one is going to be 3 over e squared. And you can continue this on and on and on. 4 over e cubed. And what's this telling us? That's telling us the definite integral we want to find. So integral from 0 to infinity of floor x e to the 1 minus floor x dx is simply the sum sum of all of this all the way to infinity. So 1 plus 2 over e plus 3 over e squared plus 4 over e cubed and so on. And I'm going to ask you, how do we evaluate this? And you may say, is this a geometric series? And it's pretty close. It's almost a geometric series. And the reason is you're multiplying by 1 over e each time, right? That's certainly true. But the top is changing also. You're adding 1. You're adding 1. You're adding 1. Huh. You're adding and multiplying at the same time. Is there a special name for this kind of series? And yes, there is. Arithmetical. Arithmetical. Geometric series. I think there may be a hyphen in between, so let me put that in. Geometric series, and it's appropriately named because you have both of these going on from term to term. You have arithmetic series going on, 1, 2, 3, 4, and you also have geometric series going on, multiplying by 1 over e each time. And the easiest way to simplify sum of infinite arithmetical geometric series is to utilize the method of multiplying everything by common ratio. And what do I mean by that? Let's say the entire thing equals to s, and s is standing for sum. So let's say s is equal to 1 plus 2 over e plus 3 over e squared plus 4 over e cubed and so on, and we want to find the value of s. And realize that if you multiply 1 over e to everything in the sum, so let's say you multiply 1 over e, so let's say you're multiplying by 1 over e to everything. 1 over e to 1, that's going to get you 1 over e. Multiply 1 over e to 2 over e, that's going to get you 2 over e squared. Do the same thing to 3 over e squared, gets you 3 over e cubed. And this thing extends on. And obviously, if you multiply 1 over e to the right side of the equation, do the same thing to the left side. So you have 1 over e times s, and which is equal to this. And you may say, how is this helping us? Obviously, now we have two equations that look pretty close. 2 over e, 1 over e, 3 over e squared, 2 over e squared, 4 over e cubed, 3 over e cubed. Okay, but nothing seems to be canceling out right away. But let's still try a common theme in mathematics, subtracting. So let's try subtracting s minus 1 over e s. So you have s minus 1 over e s on the left side, and on the right side you have 1 minus 0, let me look at it like this, plus 2 over e minus 1 over e, which is 1 over e, 3 over e squared minus 2 over e squared, 1 over e squared, 4 over e cubed minus 3 over e cubed, which is 1 over e cubed. We're still not getting a value, but, do you guys see it? What is this? What is this? You guys should be yelling with jubilant joy right now. All of you guys should be so happy that you're going out to buy more popcorn that you first bought when you started watching this video, I'm guessing. Because this series is geometric series, and we know how to evaluate infinite geometric series. Realize that we started with arithmetical geometric series, and by using this method of multiplying everything by the common ratio, we got geometric series. Beautiful. Let's continue. So on this side you have s times 1 minus 1 over e. I'm just factoring s out. And sum of the infinite geometric series is a over 1 minus r. And a is the first term, and r is the common ratio. I can prove this, but I'm not going to do so in this video. And in our case, the first term is 1, and the common ratio is 1 over e. So let me write that down. A is 1, and the common ratio is 1 over e. So let's try that. So a is 1, and common ratio is 1 over e. So you have 1 over 1 minus 1 over e. By the way, you guys can prove this equation by doing the same thing we did. By letting the entire sum be s and multiplying by the common ratio, you should be able to prove this formula. But I'm not going to do so. Let me continue. So s is going to be, you gotta divide by 1 minus e squared, but you already have 1 minus e squared to begin with. So let's just square that. Beautiful. Okay. So we know this expression is 1 over 1 minus 1 over e squared. So now let's find our answer. I am so happy, and I bet you guys are too. We know this expression is e. We know this expression is 1 over 1 minus 1 over e squared. I think that's what I wrote down, right? Yes, I did. So our final answer, if my screen stops messing up, is going to be, our final answer is going to be e minus 1 over 1 minus 1 over e squared for this fascinating, marvelous question of mathematics.